Today I'd like to talk to you about infinite geometric sums. And to do that, we're going to look at the finite geometric sum formula, which was the sum will equal the first term times 1 minus the ratio to the n divided by 1 minus the ratio. So we're going to take the same formula, and what we're going to look at is if we increase this n as many times as we can. So we are examining this part of the formula. So here's what I've done. I have this piece of paper, and I'm going to cut it in half. And then I'm going to put half of it up here on my desktop. So right now I have half of it, which is 0.5, so I have 0.5 on my desktop. Then I'm going to cut that in half. So half of a half is fourth, which is 0.25, and I'm going to place that 0.25 piece up here with the 0.5. So that means I now have 0.75 of my entire sheet of paper. And I'm going to repeat the process again. Half of a fourth is an eighth, which is 0.125, and I'm going to place that on my desktop. And then I'm going to do it again, which is 1/16, which is 0.0625. Let's see here, that if I add 0.125, I got 0.875, add 0.0625, I get 0.9375, half it again, gives me 1/32. Which is 0.03125 added to my 0.9375, gives me 0.96875. And if I continue that one more time, I have 1/64th, which is 0.015625, added to the 0.96875, gives me 0.984375. So as you see, as we continue to increase our n, what is this getting closer and closer to? 1. The most I could get on this desktop by continually halving is the one whole sheet I started with. So this part of the sum will always converge to 1. So then to get an infinite sum, I have a sub 1 times 1, which is a sub 1, over 1 minus r. But what did I do to get that? My r was always a half, and that is a ratio of decay. So as long as I'm only adding a little bit more, a ratio of decay, I will get a sum that converges. If I have a ratio of growth, I don't get a convergent sum. My sum will continue to grow and grow, thus not reach a final destination. For example, if I have 1 and then I triple it and I put it up there, I now have 4. And then I have 9, which brings me to 13 total. And then 27, which brings me to 40 total. So no matter what, my sum is also increasing all the time, not converging. So when you have a ratio of growth, something over 1, you get no sum. So when do you get a convergent sum? When you're going to infinity is when you have a ratio of decay. Then you will get a sum such that the first term divided by 1 minus the ratio gives you a total. If your ratio is a ratio of growth, you will have no sum because it also just keeps growing. So now let's use that idea of an infinite geometric sum. First you have to see that you have one. This is going from 1 to infinity, so that indicates infinite. What part of it indicates geometric? I have my variable as the exponent. That means geometric. So what is my ratio in this geometric infinite sum? It is 0.1. Is 0.1 a ratio of decay or growth? It is a ratio of decay. So I do have a sum that will converge. It is the first term, which happens to be 2, divided by 1 minus the ratio of 0.1. That is 2 divided by 0.9. I have to move my decimal place, so I have to move my decimal place. That gives me 29ths. Or those of you using your calculator, you would say 2.2 repeating. That is what this sum would converge to. Well, let's try another one. Let's say my series is written as 12 plus 4 plus 4/3 plus 4/9 plus ... Well, ... indicates infinite. Geometric would mean I'm repetitively multiplying. So from 12 to 4 is multiplying by 1/3. 4 to 4/3 is also multiplying by 1/3. Multiplying by 1/3. So my ratio is 1/3. Is that a ratio of decay or growth? It is a ratio of decay. So my sum will converge. So an infinite sum, first term, 12, divided by 1 minus the ratio of 1/3. Gives me 12 divided by 2/3. That's 12 divided by 2/3 is the same as 12 times 3/2. Well, 2 and 12 reduced to 6 times 3 is 18 is what this sum will converge to. How about this one? Isn't it infinite sum? Yes, because it goes to infinity. Is it geometric? Yes, because your exponent is a variable. So what is your ratio here? My ratio is 3.1. Is that a ratio of growth or decay? It is a ratio of growth. So will this sum converge? No, it will not. It will just grow. So we cannot say that there is one sum. How about if I give you this information? You have an infinite geometric series. Your first term is 5. Your sum is 27/5. What is your ratio? Well, an infinite geometric series is the first term over 1 minus the ratio. The sum was 27/5. So I'm going to put that in the sum spot. The first term was 5. Divided by 1 minus the ratio is what I'm looking for. So here, I'm going to do my cross products. 27 times 1 minus r will equal my other cross product, 5 times 5, which is 25. Distribute. 27 minus 27r equals 25. Subtract 27. Negative 27r equals negative 2. Divide by a negative 27. My ratio is 2/27. Is that a ratio of decay? Yes, it is. So I'm okay. A place we can use these infinite geometric series is when we have repeating decimals. So if I have the repeating decimal 0.027272727, the 27 is what repeats. So I'm going to rewrite this so I see it as an infinite series. It is 0.027 plus, I need these places filled in, plus 5 places filled in with zeros. So look at this. I have 0, 2, 7, 2, 7, 2, 7. So it'll continue in this pattern. So it is infinite. I am adding them up. Every time I had to add 2 more decimal places. So 2 decimal places is times 0.01. So my ratio is 0.01, a ratio of decay. So this will be a convergent sum. First term, 0.027, divided by 1 minus my ratio of 0.01. That gives me 0.027 over 0.99. This time I have to move my decimal 3 places. So that is 27 over 990. 9 goes into both. That would be 3 over 110. And if you punch 3 divide 110 in your calculator, you should get 0.027272727. And this is the exact work I'm going to need to see to show me, how the infinite series is working here. So let's try the 0.0416666. This part is what repeats. So I'm just going to write down my 0.041. Then I have my 6666. So I need 1, 2, 3 zeros and then a 6. Then 4 zeros and a 6. Then 5 zeros and a 6, etc. Here is where my infinite sum continues. So I'm just going to carry this along. 0.041 plus, I added 1 more decimal place,